Hello, everybody. My name is Dimitrios Liakos, and today I'm going to give you a short introduction to the compound scripting language in ORCA. So, one of the main problems in computational chemistry is that we constantly have to reinvent the wheel. What does this mean? It means that a lot of default, well-established procedures in computational chemistry are constantly being reinvented. What are the reasons behind this? The reasons are mainly technical difficulties and the absence of some default protocols. Why do we have these technical difficulties? Many reasons, but mainly it's the parsing of the computational output. You have to read the output, and this is not all the time straightforward. You have to analyze the calculation data. Somebody has then to combine data from different calculations or use different tools or different programming languages to get what he wants to calculate. Now, this is where Compound wants to help. What is Compound? Compound is a scripting language, but it can be used directly with ORCA. It combines the features of all normal programming languages, but the distinct advantage is that it has a direct access to ORCA variables. Now, as any scripting language, it contains variables, it contains scalars, one-dimensional arrays, two-dimensional arrays, it has for loops, if blocks, everything that everybody can find in a normal language. So, before proceeding, let's try to see a simple compound script and have a look of how it looks. Now, this is a very default script that will do the following. It will calculate and optimize the structure of using a BP86 functional, and then it will calculate on top some accurate DLP-NO coupled cluster energy. Now, the point here is I just want to show you the structure of the script. As you can see, in the beginning, we have some variables, nothing fancy here. Then, for each calculation that we run in ORCA, we need this new step, step end. New step means a new calculation, and step end means the calculation is done. So here we will have two steps. Then, inside each step, we give everything we normally give in any ORCA calculation. Here we have the simple input with the functional basis set. The first calculation does an optimization frequency, and the second one does a DLP-NO coupled cluster calculation. An important difference is that the first calculation contains a geometry. The second one does not. This is a huge advantage because the second calculation will immediately understand the geometry from the first calculation. If somebody needs, fine, can add here geometry too. But if not, the geometry from the previous calculation will be carried to the next one. Then, this is another thing. You can see that the 0-point energy and the electronic energy will be reading directly from ORCA. We use the read property function, and it will go and take care of all the things that we need. Finally, it has some basic math. We can get the total energy as a sum of the 0-point energy and the electronic energy. And then eventually, we can print the results in whatever form we want. And this is how a compound script looks like. Now, how we run it. In order to run it, there are two ways. Here, we will show the way where the compound script is a separate file. In this case, you need a normal .inp file like ORCA RNMP that has percentage compound and then the name of the file. Nothing more. When we give this thing, then magically, ORCA will go perform two calculations, one DFT, one DLP-NO coupled cluster, and then it will present us with the final result. So as easy as that. Now, let's go to see some real-life examples. For example, here we have some colleagues, Dimitrios and Maria Drosu, needed to know how the D-tensor behaves based on the exact exchange. This is pretty straightforward for compound. We need to write a small script, and then the script exists for all the people to use it afterwards. So we say percentage compound, and we give the name of the script. You run it, And then immediately it will calculate all the different calculations that we need, and it will print whatever we want, and will also make the plot. So this is a plot that comes automatically from the script. It's a little bit beautified afterwards, but the point is that this script that is publicly available, if somebody runs it, it will do all the calculations for copper, or you can change the molecule with this functional, and will calculate the effect in the components of the G tensor. Now, this sounds pretty nice, but once you have this thing, you can say, okay, but let's say if I wanted to see what is the effect of the basis set on the G tensor components, it's pretty straightforward. Again, we can write another script that now exists in the library. And as you can see here, we change the molecule, we choose a molecule, we choose a method, and then we give a list of basis sets and some other default information. The script will go and loop. So you see that's the important thing here. It will loop over the basis sets, and it will run each step for each basis set. It will do all of this automatically. And in the end, it will give us again a plot that shows the components with respect to the basis set. Now that this thing goes easily, we can say, okay, that's fine. But what about if I don't want to see the effect of the basis set, but let's say I want to see the effect of the functional? Now it's again the same thing. There is a script that, as you can see, practically looks exactly the same with the previous one. The only difference is that we chose the basis set here, and we have a list of functionals. Okay. Then again, exact same thing. Now the loop, instead of going over the basis set, it goes over the methods. And again, we have a plot of the different components of G tensor with different functionals. Now, let's go to do something a little bit more advanced. So now that we know that we can play with variables, one of the problems in chemistry is the convergence of energy, especially if you go to correlation. So let's say we would like to calculate the energy of the water molecule. Now here we plot the energy of the molecule with the CC basis sets from double zeta to sextuple zeta. But on the right, you see that the timings at some point become too expensive. Now, because the convergence seems to follow a pattern or a function, a lot of people found ways to extrapolate the energy based on the function that they use. Now, for example, here, using one of the known extrapolation schemes, you can see that using double triple, we're pretty close to the energy of the sextuple zeta result with the timings of the triple zeta. So this seems to be a pretty useful thing to do. How can we do it using compound? Now, with compound, we have a GitHub page where we have many, many different scripts. For extrapolation, because the function it's not unique, a lot of people have tried a lot of different functionals, and we have a list of a lot of different extrapolation schemes. So all that somebody has to do is choose one of the extrapolation schemes, one of the scripts that exist in the library, then choose the molecule, and then you can calculate the energy. So here we use the EP1 scheme. It's a very known scheme that practically extrapolates the SCF energy and the correlation energy separately. But the important thing here is that once you choose your script, compound will do everything. It will do all calculations that are needed, and it will print us the results. Now, this seems pretty nice. Then we say, okay, if we can extrapolate energy, maybe we can extrapolate the derivatives of the energies. So, for example, let's try to do, if we can extrapolate polarizabilities, that is the second derivative of the energy. Exactly same thing as before. The scripts are available. You can choose a script. You can choose the molecule. And then everything is done. So here I just present you the results. They're not really important. But the important thing here is that, again, choosing just one of the scripts, you can get all the extrapolated parts of the polarizability. And this is something that is pretty difficult. It's not very common to see. So energy extrapolation was okay, but extrapolated polarizability, it's not really known. Now, since we can extrapolate second derivative, obviously we can extrapolate also the first derivative. And let's say we can extrapolate the gradient. And nothing peculiar here again. There is a script that extrapolates the gradient, and we only have to give the geometry of the molecule. We do that, and again, we have the extrapolated gradient. Again, here we use the EP1 extrapolated scheme that extrapolates Hartree-Fock and correlation energy separately. Now, I want to show the ladder of how things can go. Since we have the gradient, this means that we can do geometry optimization with extrapolated gradients. And indeed, we have a script like that. It is publicly available, and it will use the extrapolated gradient to do geometry optimization. This would be, again, just choose the script. I will not show you this result here, but once we have the gradient with extrapolated calculations, we can think of the following. Let's do the gradient using basis set superposition error, which is something that a lot of people find difficult to treat. There is also this kind of script that will do the geometry optimization using basis set superposition error corrected gradients. Of course, the molecule needs to be a little bit different, but again, it's the same thing. Now, because exactly of the complexity of doing such a calculation, it's pretty rare that you will find in the literature geometries that are basis set superposition error corrected. We only normally correct the energy, but not the geometry. And you can see here that for the water dimer, the effect can be significant, right? We have 1.96 with BSEC optimization and 1.89 without BSEC optimization. Now, having done all these things, another thing that a lot of people do is a scan, right? A geometry scan. And this is something that ORCA already can do. But obviously now with compound, we can do a little bit in a more flexible way. So let's say we would like to see the dissociation of the neon molecule from 2.5 angstroms to 5 angstroms. With compound, we have a scan. And the name here is a little bit tricky, but means one dimension, one method, one property, because obviously we can have all different kind of combinations. And as soon as we choose this script, then the calculation will run all the different calculations, different steps. Then it will read the outputs of these steps. It will analyze the results, and it will store them. Now here we choose a CSV file, but this is up to the user because it's pretty common in the literature. After writing the CSV file, it will write a Python file that reads the CSV file and plot the results. So in the end, just use the script and you come up with exactly this graph. So I think this is pretty nice. Now, since we can do one dimension and one method, obviously in compound, we can do two methods. Let's say we want to compare, or more than one method. So this is what we did here. We have another script also available. The only thing one has to give is the geometry. And then here, as a different method, we just choose different basis sets. So we can see the potential using the different basis sets. Let's switch gears, go back to polarizability, and do something a little bit different. So we will try now to calculate the polarizability numerically. So this is a little bit tricky, but again, there is the script is there, and I will try a little bit to analyze it because I want to point to some interesting features of compound. So as before, we choose the script and we choose the geometry. Then the idea behind the script is that we have two loops, one over the Cartesian coordinates, two over the Cartesian coordinates. Then for each of them, we add a small field. The field depends on the coordinate. Now, how do we do it? We just have two loops, and the loops go from 0 to 2 because we have three x, y, z. And this will create the string for the field. Once we have this thing, inside the loops, we just run the calculation. And the calculation has everything common but the field. That's the interesting thing. Now, we can see here that we also read the molecular orbitals from the first step, but this is just for fun. We need it for the symmetry, but I just wanted to point that we can read the molecular orbitals from a custom step. The important thing here is that inside the loop, we calculate the energy of the step. Then, in the end, we have now the raw alpha tensor, the raw polarizability tensor that we construct based on this formula. The more interesting thing is that compound has also some basic linear algebra functions, like the diagonalize here. And once we have the raw I tensor, we call the diagonalized function, and this returns the eigenvalues and the eigenvectors. Once this is done, it will print everything for us, and this will give us numerical polarizabilities. Then let's go to something a little bit trickier. So here we want to make a library of the electron densities of free atoms. How can we do that? So we give a list of elements, as you see, whatever elements we need. We give a list of number of active electrons because we will use CASSCF at some of the calculations. We give them a list of number of orbitals that we will use in the CASSCF or in the Hartree-Fock. We give a list of the number of roots. Then the charge, multiplicity, the Hartree-Fock type, if it's CASSCF, RHF, and then immediately we have this small script that will calculate all the electron densities for all the atoms we gave. Let's have a little bit of a look here. So what do we do here? We loop over the elements. And as you can see, we don't even have to give the exact name because it can also already read the size of the list of elements. Then we check if the Hartree-Fock type of the corresponding element is a CASSCF or not. If it's CASSCF, we do the CASSCF calculation. If not, we do the Hartree-Fock calculation. And that's all. And this will create immediately a list of all atomic densities. Next, so something a little bit funnier, but just to show a technicality. So compound also uses the go-to function. If we need, we can do it. So let's have an idea to invest some precious research time to write a totally useless on-off switch. This is a great idea. So what do we do? What I want to show you here is the go-to. And you see that we can have a go-to function even inside an if. And we define some label, turn off, turn on. And this is all. That's the whole script. There's nothing more. And if the switch is on, it will go to turn off. If the switch is off, it will go to turn on. And in the end, it will turn off and on the switch. But the point is, we have also go to. So one last thing from scripts. One of the most useful things in computational chemistry, obviously, is spectroscopy. This is the identity of the molecule, right? And spectroscopy is not as trivial. So normally it has a lot of steps. It has a lot of different kinds of calculations. Now, this is a script that Dimitrios Maganas wrote, and it will calculate the XMCD and XAS spectrum. What it will do it will compute the initial QRO orbitals in DFT level, at DFT level. Then it will perform a state average CAS-SCF calculation of the valence space. It will rotate orbitals in the active space and do an FPT2 on top of that. And then it will also call the ORCA map SPC and generate the spectra. So as you can see, it will do all the steps. The only thing one has to do is give the geometry, call the script that it's available, maybe give some details about what orbitals we want to rotate, and that's all. Now, let's move to something a little bit more technical. Every time a user performs an ORCA calculation, ORCA creates a normal ORCA output, but also creates the property file. This is what compound reads to analyze all the data. And so let's have a look on the property file, because it's an integral part of compound. Property file is a text file, right? So the user can also open it and play with it. It contains information of the ORCA calculation. The difference is that now it is in standardized format that is more easy to parse and standardized from ORCA. Now, the aim of the property file is that first we want to use it for compound to get all the information we need. But then the property file can also be used as the medium step from other programs to interface ORCA, right? Let's see now how it looks. So there are details about property file in the ORCA manual, but more or less the idea is the following. Every property file in the beginning has a header that contains the version, and then we have $1 for each property. And each property has a name and then an end. So $, property name, and then an end. And this has a new property. I would like to say that we have more than 250 properties now in compound that are stored in property file, in ORCA that are stored in property file. Now, inside each property, with ampersand, we have different components of this property. So each property might have more than one component. And each component can have a type, an integer, be an integer, have a different dimension, have units, have different kind of stuff. All these are documented in the manual. Besides the property file, there is also a more general module in ORCA that is, thanks to Dagmar Lenk, that can create JSON files from ORCA. And property file has a format based on ORCA, while JSON has its own libraries. It's a standardized format in the industry, and languages like Python can know immediately how to deal with it. So people might want to use JSON. So what ORCA to JSON does, it can convert to JSON format first all the properties of the property file. So whatever is in property file, using ORCA to JSON can immediately be converted to JSON. It can have informations about basis sets. It can have informations about the geometry. It can have now the molecular orbital coefficients, and then, and most important, it can have all the 1 and 2 electron integrals. Then, in addition, it can have some CIS amplitudes and the calculated electron densities. Of course, it can have some charges. So practically, a user can perform some ORCA calculation, get the 1 electron integrals, get 2 electron integrals, get some information about the orbital coefficients, and play around and create some different methods just for fun. Then there is one additional thing. ORCA to JSON allows the user to create a GBW file, the file that ORCA reads to make the calculation, from a JSON file. So you can also do the reverse. Get a JSON file, and from that, create a GBW file. So that was all from me. This is ORCA, this is compound, and the details about property file and ORCA to JSON. I hope you have some great time with it. Don't forget that there is a library of compound scripts in GitHub. They're available, and we would like people to go there and add some new ideas they have and some new scripts. Have a nice day.